My brain got derailed on the way to opening OBS. 2 minutes before the stream started, I said I should start getting the AV gear ready. I turned on the camera, I focused it, I then forgot that I needed to keep going with that job. I didn't open OBS, I didn't open Companion. I got distracted by stuff on the RepRap Micron on the bench. So, yeah, I suffered a squirrel attack on the way to pressing the stream button. I acknowledge the traditional owners of this land, the Whadjuk Noongar peoples. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. I hope everything is good. Yeah, RepRap Micron gets you that way. Yes. Pete, we are there indeed. We are. We are. Who? I have Castnode open. I have a list. So, good morning to, I was going to say no particular order, but this is the particular order that Castnote decides to show them to me. Michael Wires, Crispian, Princess Fiona, Vic Oliver, Stephen 44799, Wagon Loads, David Crisp, John Whips, Emmy is here, Simon CBR, Tinker, Grant Maisels is here, Eddie Mules, Gavin Jackson, Pete. Welcome. Watching on delay today, says Stephen George. Do you have better things to do than hang out with me? I don't think you do. SK Photo Guy, good morning. Tinker says, if a squirrel were to eat all of the nuts on your bench, could you then trap him using a big magnet? Yes, is the direct, no beating around the bush answer. If a squirrel ate all the... Okay, so these are all the nuts. Not all of them, but this is most of the nuts on the bench. They're steel. They are steel. A magnet, yes, indeed, he would grab onto them, and if it was strong enough, it would grab onto them through the squirrel. Wagon Load says, get RepRap Micron to push the start button. Okay, so, not if they are stainless steel, says Simon. That is true. Yes, mild steel would be okay, but stainless steel, not so much. 36 months for Pete brings us this music. Pete, 36 months as a silver supporter member. Thank you. Okay, so yes, Tinker says we may have a squirrel solution then. All right, going back in the chat. Okay, I'm going to declare chat bankruptcy and get into stuff. So the big news of the day. Hang on, I'm going to get. Do I have Facebook? I better close that before I switch over. I've got a chat. Pete, stop it! That is Pete dinging my doorbell through the phone. Crispian! I can't compete. Oh, what? Pete's a laggard. Tinker is outdoing Pete. 40 months. Okay, so this is, we're playing it on repeat. So thanks again to, that message was DHL saying I've got to pay import duty on a shipment. Damn, I must have gone over the threshold that triggers the you've got to pay money, which unfortunately can be done in aggregate. Before I get onto that, so recapping, thank you to Pete, Crispian, and Tinker for those memberships. What am I saying? Yeah, there is a certain threshold under which customs does not care. Basically, you do not pay import duty on stuff, and although they could legitimately charge for it, but they just don't bother processing it. I think there's a difference between the point at which you are legally required to pay import duty and the point at which they actually charge import duty. And so you can get you can place an order, and sometimes it'll get import duty, sometimes it won't, and it just depends on a number of things. Part of it, I believe, is aggregate order value within a certain time frame. It's a certain amount per month. So I might order $500 worth of stuff from DigiKey, and then a week later order $700 worth, and then a week later order another $700 worth. And in aggregate, like, each of them is below the threshold that will make them go, ooh, you got to pay for this. But then I place another order for $500, and all of a sudden it's like, you got to pay import duty, because the aggregate was exceeding some thing that went ka-ching and raised a red flag. And I believe that is what has just happened, because I have been ordering a lot of parts over the last couple of weeks. Tinker says, I got a very handy toolkit from China today and paid no shipping or import duties. Yeah, nice. A very handy toolkit. Tinker, tell us more. What is handy about this particular toolkit? I have to zoom in on chat so I can read it more easily. There we go. Now, this, I have a list of things for today. I am going to do some RepRap Micron stuff. I have it here on the bench. I was messing around with it just before the stream. And maybe a couple of other things as well. The big news is, let's see if I switch to this. Vic sent me a message yesterday saying that he has hit a particular milestone, which is not that one, this one, reaching the feature size of the Intel 4004 microprocessor. So this is the making two tiny dots. All right, so this is the current probe configuration. You can see there in the picture, and you can see this is a bit indistinct. It's pushing the limit. So Vic said, yep, definitely pushing it here. Limit seemed to be in the substrate and tip, not the RepRap Micron. Backing up. What the hell am I talking about? So what we are looking at here is Hello World. In fact, I'm going to come back to here for a reference point. So this is the photo that has been used for a little while now for showing the capabilities of the RepRap Micron. So this is Hello World, which has been, I suppose you would say, etched into some ink. So this is a glass microscope slide with Sharpie ink over it, which is that purplish color you see. And then the tip of the RepRap Micron is pushing dots into the ink and pushing it out of the way, essentially. So it's like stipple embedding into the surface of the ink, because the ink is very, very thin. And so this Hello World, the entire thing is 1.3 millimeters long. So that is very, very small. Think about 1.3 millimeters, and all of this fits within 1.3 millimeters. Yeah, mid-2025. So this is sort of the benchmark of where things have been up to. And so this was written a little while ago. And the goal was to hit the feature size, like the 10 micron sort of resolution. Terminology is possibly not quite right. But what we're talking about here is the Intel 4004 with 10 micron feature sizes. And Vic's goal has been to get down to the point where he's working at that scale. down at the microprocessor feature size sort of level. Vic said, feature size means a thing and a gap between the next thing. Yeah. So, yeah, when you talk about process sizes with current, you see all of these numbers. People talk about what is TSMC's current feature size and what is the, like, how many nanometers feature size is the current, like the current Apple silicon chips and those sorts of things. But the thing is that you can't reduce it to a single number. Yeah, as Vic says, the numbers lie. Henrik! 25 months of membership. Thank you, Henrik. Okay, so also in the chat, I said hello to Stephen George earlier. We have SK Photo Guy, Tech Nebulous, Henrik. Thank you for joining. Yeah, that it is not like a grid at a fixed size. The numbers are far more nebulous than that. So if a fab says, oh, we are building this with a 5 nanometer, on a 5 nanometer process, what that 5 nanometers actually means is not is not that clear cut. So it's kind of it's borderline marketing numbers taking over from the complexity of engineering and physics. And so when the stats say that Intel 4004 was made on a 10 micron process, yeah, it doesn't necessarily, it's the like the gaps between things, the widths of things, all of those have different characteristics. So yeah, anyway, the point being, this was 1.3 millimeters across. Okay, now check this out. So Vic's new, so June 6th, yesterday, this was what Vic was getting to. So, yeah, once again, Sharpie marker, and this is with 8 micron spacing, looking through the Conus microscope. And so the whole thing is 56 microns tall. So the entire thing, it is hard. Let's pull this out so that we can put it side by side. I'm going to stick this one over here and this one here. Okay, we are really getting into the point now where it becomes hard to comprehend, because it becomes below, it's way below the point where you can look at it and get a sense of scale. You're looking at it through instruments or through optics, which means that you can't tell the difference between something that is small and something that is really, really small. So with this Hello World, you can use your bare eyes and look at the slide, and you can see that there is a little mark on the slide which is 1.3 millimeters long. You can't necessarily read it with your eyes, but you can see that that thing is there, depending on how good your eyes are. But this is crazy small. So this is, once again, Hello World, and you can see that it's less distinct, but the whole thing is 56 microns high, and as it says here, that is the size of the spacing between the dots in this one. Henrik! Henrik, what was it? Henrik said, hello world, should I say hello world and goodbye? Oh, does that mean that you are heading off to bed? Because it is early. It is definitely dark o'clock up there in the northern hemisphere, in the particular place where you are, in the location where you are. Yeah. Henrik, thank you very much for the popcorn. Yeah, so, all right, once again, get this into your head. This is 1.3 millimeters long, consisting of these dots. This entire thing, the height of it, is the spacing between these dots. That it really is getting into the point of your brain cannot grasp the scale of these things. So zooming in with the Biolux, so this is so there are a couple of different sets of optics and cameras and stuff involved here. So they're zooming in on the gory detail with the Biolux. No, it's not late, not early, and enjoy the popped up corns. Okay. Yeah, so for scale, for those of you who don't work in metric, Wagon Load says the length of Hello World in the first one is close to the thickness of a US penny. Yeah, so from here, the start of the H to the end of the D is the thickness of, like, the edge of a US penny. So you could write that across the edge, not around the edge, across it. And then this fits into like a spot that's so small on this picture you can barely even see it in the picture. I don't know, when I first saw Vic's RepRap Micron project, it blew my mind. I thought, this is incredible to be working down at this sort of scale, and this is so much further beyond anything that he was showing previously. So yeah, it is kind of nuts. It is kind of nuts. So I'm going to, yeah, Jono geeking out on reps, exactly. Need cash to just figure out sizes. Oh, that reminds me of a little video I saw a couple of days ago. As Tinker said, poor Americans stuck with such a bad measurement system they need cash just to figure out sizes. Yeah. Yeah, there was some comedian who was doing a show in Canada, and he was asking them about units and whether you use kilograms or pounds and inches and millimeters, and it's like, if you're talking about someone's height, it's always imperial. If you're talking about something else, it's metric, and speed is in speed is in kilometers per hour, but distance is in time. Like, you don't say the distance of how far away something is, you say, oh, that's 2 hours away, or that's 1 hour away. Yeah, trailer camp metric. Stephen says, John had hair, he could be leaving notes on them if he finished his. I could be using using a piece of my hair to write messages on. Using this. Oh. Yeah, Pete says Australians tend to measure distance in time. That's true. Yeah, if someone says, oh, how far away is Knox from here? I would say, oh, it's about 10 to 15 minutes. Yeah. Yeah, SK Photo Guy says, as a Canadian, that is spot on unless you are talking to older farmers, in which case they use miles, partly because of the grid road system in Saskatchewan, Manitoba and Alberta. HTML, hair text markup language. Yeah, we can we can overload that. Did my last comment really have a bad word in it? Where is that? Michael, where was Michael's previous comment? Michael? I didn't see anything. I didn't actually even see it. Where is a comment from you? I can't see anything in the chat. Strange. Okay, so my goal now is, let's get an axis moving on this RepRap Micron. I have parts sitting beside me. I have a little bit of prep work that I did immediately before the stream. So I think we can perhaps get one of the axes moving. Oh, Michael says, let me repaste. Okay, go for it. Because I could not see a previous message from you. Oh, Michael said, which is why motorsport gaps are measured in time, not distance, because speed of cars varies. Yes, that's true. And this time it worked. Yeah, I don't know why it didn't work before, Michael. Okay, so looking more at Vic's blog, limits seem to be in the substrate and the tip, not the rep micron. So it sounds like the mechanicals of the structure of the thing, like this thing that you can see right here, are capable of doing this, but the substrate and the tip structure are now becoming the limiting factors, the mechanical limiting factors in this. So takeaways: Picker, the print-in-place kinetic assembly, something like that, with a touch probe is going to be up to positioning the probe as accurately as is needed for sub-10 micron features. Need to get the touch probe design put in the repository, put a wider tip on it to begin resin deposition on the 10 to 20 micron scale once more. Okay, this brings up an important point, which is Vic needs some samples of conductive UV resin. So I'm going to put an appeal out for this on Mastodon or wherever I can get the appropriate people interested. So now that Vic has got the mechanical part of this working down to that sort of resolution, he needs to switch back to doing resin assembly rather than scratching in the ink. And to do that, he needs conductive UV resin, which is really hard to find, really hard to get. Because with conductive UV resin, he can now start doing fun things with making electronic circuits at this sort of 10 micron scale, 10 to 20 micron scale. And that is going to be that is going to be a serious milestone. So if anyone has a lead on how to get hold of samples, because the volumes required are tiny, we're talking, milliliters would let you do a whole lot. When you're working at this scale, the amount of material you need is literally microscopic. So if anyone has a source of conductive UV resin, please get in touch with Vic. So blog.reprap.org should give you a starting point for getting in touch with him, or me, and yeah, let's see if we can figure this out, because I really want to see Vic be printing electronic circuits at the 10 to 20 micron scale. That will be nuts. Stephen says, would you need both conductive and non-conductive to build circuits? Potentially, but the non-conductive is largely solved, I believe. Like non-conductive UV ink could be, can be done. It's the conductive UV resin that is hard to get your hands on. Well, even harder than the non-conductive. Yeah, so I can just imagine it like a dual tip system. No, you can do a lot. If you're not trying to cross over traces and insulate between them, then you could lay out a circuit in a totally 2D space using just one probe and conductive ink. Oh yeah, Vic has just posted his email address in the chat. vik@diamondage.co.nz. So if anybody wants to, if anybody has a source or a clue about where to get conductive UV resin, please speak up. Wagon Load says, what about pencil lead filings in hot glue? In hot glue? I would think that, well, not hot glue. I would think that it would be better to mix it into UV cured non-conductive resin. The conductivity of it would be fairly low though. Vic says you can have 2 resin reservoirs. Cleaning the probe between is left as an exercise to the diligent student. Yeah, imagine trying to have a mechanism to wipe off the probe when the tip of the probe is down to atomic atomic scale. Vic says pencil lead shavings and resin are like rocks in custard. Yeah, Megan Lead says iron filings. The problem is anything that you could produce yourself is unlikely to be fine enough to do any of this, because scale. It is hard to get your brain around how small this is. Yeah, we are talking about getting down towards the atomic scale here. So anything where you like grind some material up and try to mix it, it's going to be, yeah, yeah, not quite down into that region. Tinker says, think individual molecules. Yeah. Yeah, so conductive UV resin at this scale, hard to do. Very hard to do. And hard to buy, because Vic hasn't been able to buy any. All right, now. Oh. Okay, this is going to, in a moment we are going to do this, but first, oh, which reminds me, hang on, I want to see if I can find this. Where is it? Paul, I want to see if Paul's But First module is still on. Oh, this is from 2008. Sorry, I am. Oh yeah, so Dr. Conway. I know Kung Fu. Sorry, I am quickly scrolling down through. Through Paul Fenwick's blog from 2008, trying to find some where is it? OSCON, OSDC. Nope, not there. Results from the CPAN. Maybe I should just have a look in CPAN. You have no idea what I'm talking about, do you? That's okay. Chat among yourselves. I am... Oh, here we go. The But First. And when was this published? I'm not sure. I'll look it up. Oh, where was the date? Oh, this was from 2005, September 21st, 2005. Yeah, this is a squirrel off a squirrel, because what I was going to talk about was the push-up challenge. So this is something that Paul did, yeah, way back in 2005, 21 years ago. He wrote this, and oh, see also, wink, 404. Oh, the Sydney Links user group page is gone. So this is a Perl module that Paul wrote so that if he was writing some code and then realized that he should have done something before the thing that he has just done, he doesn't have to move back and write it further up. He can do, but first do this. So print a greeting, but first find caffeine. So when it comes to this block, it will defer execution of that block. You probably can't even see that. it defers execution of this block and executes this one first. So, so it'll say what this will, if you execute this, it'll print, I need a coffee. Good morning. Paul is such a twisted human. Print our lines, but first reverse them, but first convert them into uppercase. While print, but first reverse, and then but first uppercase. So you, it's converting them to uppercase, and then it's reversing them, and then it's printing them. Okay. I have amused myself for a few seconds now. Yeah, so there was, Paul revealed that at OSDC.
Run it on a multi-threaded system, infinite loops.
Run it on a multi-threaded system. Perl, I believe, is not multi. Maybe it is. Is Perl multi-threaded? I don't think so. I don't think the runtime is multi-threaded. I could be wrong. It's a long time since I've done any Perl stuff. It'd be back in that era. The last time I looked at Perl would have to be 15 years ago, maybe more like 20 years ago. At the very minimum 15. And that would have been, pulling up something that was old to me at the time. So, as you can tell, my brain is malfunctioning. I should do something to improve my mental health. And so, push-up challenge. Okay, I am going to drop this in the chat. For those of you who have not heard of this, this is an annual fundraising and awareness raising exercise, where a bunch of silly people basically commit to doing push-ups. How many is it? It's a lot. I don't want to know because I'm doing them. Where are we? Yeah, you do 3,307 push-ups between 3rd and 26th of June. And it's one of those, awareness. What am I saying? I'm repeating myself. Yeah. A whole lot of people are doing it. 223,000. $6 million raised so far. And 50.5 million push-ups. Although, I'm not sure if this is total over the lifetime of the program or if it is so far this cycle. I don't think it's so far this cycle. So I'm with some nerdy Canberra friends in a team, because you can do it solo or you can join a team, and then that way you get to see how much other people have done and challenge each other, basically. So if you want to, if you feel like it, it's probably not too late to join the challenge yourself. It's been going for a few days now, and yeah, if you feel like donating, please. The Canberra Thursday Nerds is the team, and there's a challenge. Where is it? Funds raised. Yeah, look at this. Tessa's winning with $505 raised. Got to beat Tessa. So that's the challenge. So donate, please. Tinker says, I quit doing push-ups when I left the military 40 years ago. Yeah. Michael says, the push-up challenge was popular at my previous employ, but I refused to compete on principle. The principle of old age and failing joints. Yeah. Yeah. So, okay. What are we doing? All right, I'm back to my list. Now, what have I mentioned on my list? I actually have a list this time. So I've talked about VIX achievement. I've talked about the conductive UV foam. I have talked about the push-up challenge. Okay, people, nerd brags. Oh, here's one on the list. Now, last week I believe I talked about discovering what the structure of a fusion file was, but I did a thing, kind of. Let's see, code. So I'm going to do a little demo. Where are we? Hang on, oh, that's the wrong thing. I went to companion. I want to go to, oh, hang on. Companion has taken over port 8000. Ooh, okay, so because I'm running companion right now, I may have to change the port. Oh, no, stuff it. What I'll do is load, register, portal test, there. Okay. 2 no, I want to go to designs, test automatic. I want to demonstrate something to you. Oh no, I haven't updated the code on that. Register is still running the 02.1 software. Alright. I may not be able to show you this right now, unless I change the port that something is running on. It's probably not worth it. I can show you next week. I'm going to give it a couple of seconds of attempt at getting this up and running. Okay, got to bring up my VN, and yeah, I know you can't see this. I'm getting there, and I have to be a little bit careful about what I show in this terminal. All right, PipeRaj. Where is the port defined for UWSGI? Let's find it. Port 8000. No, don't find me all of those. Just polluted my grep. I must tune my grep. Or I'm just gonna grep into less. That'll help solve it, I think. No, there. Binary file, API, where, no, the API, ooh. Oh, I might break things. No, probably not. Like I said, go and talk among yourselves while I figure this out. Stop that. Quit. Okay. Where is the config for that? It is in PipeRaj. That, and is it in local settings? No, the port is not defined there. It is. Yeah, this is one of those things where I could find it with a little bit of time, but Ooh, or I could update the version that's running on the VM on Linode. Yeah, I didn't realize that companion. Okay, forget this. What I'm going to do, there is a much simpler solution to this. I'm going to quit companion. Yes, indeedy. Companion, you can go bye-byes. Which means I am going to lose my ability to switch scenes in OBS. Well, doing it that way anyway. So, instead, I'm going to do manage run server, go. Okay. Let's see if this works. 127, port 8000. Yes, it is working. Designs, test-o-matic. And I'm going to do a bit of cleaning up here. What I need is a bulk delete. I haven't done that. The only reason I actually need a bulk delete on this stuff that I'm doing now is for this sort of situation where I want to replace everything. Alright, now, designs, dashboard. I'm going to throw this up here. And so this is the register. But before I show you stuff on that, I'm going to bring up this and bye-bye fusion extractor. Yeah, so this. Okay. Last weekend I told you that hang on. Are you screen sharing? I was deliberately keeping it off there. He has a list. Fusion extractor, yes, Princess Fiona called it out. Okay. Oh, Vic says, I think I've done my nerd brag. Yes. Vic has banked nerd brags for life. There are no more required. But that won't stop him from doing more things that are brag worthy. Yeah, last weekend, I believe I showed you, although I can't remember. Did I show you that I was messing around with Fusion project files and I discovered that they were a zip containing other zips and so on all the way down, and they actually contain a whole lot of things. So I've made a Python library which lets you bring in a Fusion file. So you can say, I want to open this .f3z, and then you can get information out of it because there is embedded stuff in it. You can pull the project name out of it. You can find the size of different attributes, the attributes of different assets that are within it, because it contains the schematic, the board file, both XML format, preview images, so you can return a Python list of the sizes of all of the preview images. You can return the size of the bill of, no, that's not the size, that's the bill of materials, which it extracts. So there is no bill of materials stored within a Fusion Electronics project. Just to clarify, this is not something that is in there that we are sucking out. This is being generated dynamically by the Fusion Extractor library, because what it does is inspects the XML, so the schematic and the board here are just XML, and it finds all of the part definitions that are within those, and then it compiles its own bill of materials, which comes out, which you will see in just a moment. So it generates a bill of materials from it. You can dump those out to disk. So you can say, for example, you can call a specific thing, like I want to extract the schematic, or I want to extract the board, or I want to extract previews, or whatever. And you can either just tell it to stick it in a target directory. Once again, I should have zoomed in. Insufficient zoomage. Oh, here we go. Yeah, you can tell it to just stick it in a specific directory and it'll make up the file name. The actual assets inside the project file are stored with names that are like basically a UUID. It's just like a long hash with dash separators. So you get the original like UUID file name coming out, or you can specify it, and things like the name of the project are exposed by the library, by Fusion Extractor. So you can do substitution. So for example, you could specify output and then project name as a variable .board, and it will dynamically construct the file name based on the project name. So that's all supported in the library. Oh yeah, destination path behavior, all written in here. Board images, you can specify PCB top, 3D bottom, so it's got renders in it. Preview images, it explains how these come out, so it generates a list of the preview images. Reference is there. Oh yeah, bill of materials. So get BOM parses the embedded XML and then generates in this sort of format. So you can see, yeah, well, not in that format. It comes out as a list, as a Python list. So in here we've got 4 entry in project get BOM. So we are stepping through the extracted bill of materials, each one being an entry, and then entry.reference, entry.device, etc. With, in this case, it's just printing like that. You can CSV it, whatever you want to do. Yeah, so that is zoom and enhance, yes. Right. The reason that I did this is I wanted to build this functionality into the register, which needs a new name. And I'm just wondering if I should mention what the project code name is. Through a very funny conversation. No. Through a very funny conversation, there was a conclusion about yesterday about what the code name for the register project could be. So if I have a look at GitHub, where are we? Register. This one. This is what I'm talking about. At the moment, it's just called register, but it needs a more complete name. So this is the software for managing production of circuit boards. And you can see a screenshot of an old version of it there. It has developed a lot since then. There's a bunch of discussion about restructuring and, rename the project. So the actual running version, where is it? Okay, this is a dev version that is running on my local machine. And so we've got designs, boards, organizations, which is going to get renamed. Boards is possibly going to get renamed. New sections are about to be added in here, like ERP functionality is going in here. It's also about to be refactored into separate Django modules. So yeah, lots of development going on this right now. So designs, if I come into designs, you can see I've got a whole bunch of Superhouse designs here, and I can search for Testomatic. There it is right there. Click on that one. So this is the record for the Testomatic design. And you can see it's got 3 boards with serial numbers that, sorry, 5500, it's out of order. 5500, 5501, 5102. No, it's not out of order. What am I saying? My brain misfired. So that is in serial number order. And it's got an assembly guide, pre-packing guide, which are both images, I believe. And here you can see there are a whole lot of attributes or design files associated with this project that could be stored against it, and they are not here. Not uploaded is what it says. Hang on, I wonder if I can get some more zoomage on this. I should get more zoomage on this. That's enough. So, so what I did was implement some upload functionality here. So you can add random attachments, like if I wanted to just, I don't know what this is going to reveal in my file selector. Ooh. Okay, let's go to there. How about to here? How about camera? What am I going to look for? Not that this matters. What am I doing? I should be doing this off stream. Yeah, stuff it. I'm not gonna bother uploading something. But anyway, you get the point. You can pick something, upload it. It ends up attached to the design. So that could be anything. It could be a PDF. It could be a text file. It could be an image. It could be a data sheet. Whatever. I don't have URLs as an option. Interesting. I hadn't thought of that until just that moment. But it probably doesn't matter. So here, what you can do is, imagine you want to upload a bill of materials for this design. You could go upload, you could choose your bill of materials and upload it, and it would end up here. So the bill of materials is going to be very important when it comes to ERP and doing batch planning, because the system is going to need to know what parts are in stock. So it needs to know how many 10K 0603 resistors I have and how many whatevers. And then when a production batch is queued and I say, I want to build 10 Testomatic V2.3s. So there'll end up being a button in here which will be like add to batch, or like a whole order ingestion process as well, where stuff will get added to orders, to production orders, so they can go into a build queue. And it needs to be able to multiply out the quantity you want to build against all of the items in the bill of materials, so that it can figure out if you have enough parts to build it and what the cost is going to be, and if you have any shortfall. So if there are parts that you do not have that you need to complete assembling that batch of boards, you would need to raise it and say, you've got to order more whatevers, and lead times and all of that sort of thing. So the way this is structured right now is, if you wanted to, you could upload a bill of materials. You could upload a PCB design file, you could upload a schematic design file, so that could be like a KiCad file, like a KiCad PCB file, KiCad schematic. Doesn't matter. You can just upload files. You could upload a picture to show what the thing looks like, upload a firmware binary. I am rethinking this. I'm going to split binaries out. Like firmware is going to move into a whole extra section. There is going to be a section here for testing, and that is going to include the test definition, which will get pushed down to the, or pulled to the test chassis, the Testomatic, and it's going to, which will also reference binaries. And often there will be multiple binaries. You might have one binary that you install on your target board for testing, which is going to exercise functionality and have debugging enabled and output statuses and things, so that you can see that it really is working properly. And then once you're done with testing, load a release binary onto it, which would have debugging turned off and not necessarily output as much to the serial console or anything to the serial console or whatever. And also there are many projects that I work on that have multiple MCUs. There is a project, it's really common for me now these days to build boards with at least 2 MCUs on them. I've done many designs which have an ESP32S3 and an ESP32H2 on the same board, because what that allows you to do is thread and wireless networking at the same time, and you can offload the thread mesh networking to the H2 as like a co-processor or a sub-processor, that just handles the mesh network and have all of the application logic running in the S3. So you need to be able to load firmware into both of those microcontrollers, which you can achieve by embedding the H2 firmware into the S3 firmware. But it's also really common for me to have things like an ATmega 4808 on the board as a dedicated sub-processor for dealing with high-speed I/O, like watching interrupts on motor position encoders and then just reporting back to the main processor. So the main processor is dealing with the overall application logic and running an RTOS, which is dealing with all of the scheduling, and it talks to the sub-processor and gets encoder values and things, but it doesn't need to be dealing with every interrupt that comes in thousands of times a second from the encoders. So anyway, point of all of that, firmware binary does not belong here. There is going to be a whole extra section. So we're going to have the overall information about the device, the project, the design files for the project, which are right here. There will be attachments, which are arbitrary things, and there will be testing. So there's going to be a whole new testing section in here where you define all of the tests, and then boards, which are the actual boards. So this is one I built on 21st of September 2025, and all the details of that specific one. So point is, you can upload individual things, or you can pick Fusion Electronics project. Let's see if I can find, where am I going to find, oh, I know. There, if I go to here, and source, and Fusion Extractor, is it in here? Temp, yes, okay, Testomatic, here we go. So, this is the .f3z file for Testomatic, and I've selected it. Haven't yet uploaded it. So as you can see, we have nothing populated. We have none of these files, and we don't have any preview images or anything. So all I'm going to do now is click upload, and boom, done. So now we have a preview image. This was extracted from the Fusion project, and then down here you can see that it has populated all of these. So like PCB bottom view is there, PCB 3D view, it's very scaled down, it's only a thumbnail, is there. We've got the design file in Eagle XML format, like the PCB file, schematic file, bill of materials. Yeah, it's all of this has been auto-populated from the Fusion project by using this. So, if anybody is messing around with Fusion and wants to process the and wants to be able to process those files, extract them, mess around with what's inside them, check out Fusion Extractor. Available from a PyPI near you. So, yeah, and bill of materials, this is the one I was talking about. And you can edit stuff about them as well, like PCB bottom view. I could go edit and add a description to it and change its name and that sort of thing. The name was auto-populated from the project name and stuff. But you can edit it if you want to. So bill of materials, I have just downloaded that, so now show in Finder, open. Let's open the bill of materials. What is it going to open in? Oh, okay, it's opened in numbers. Thanks, macOS. There we go. The table data was imported and can be adjusted. Can I? What? You can't Command Shift plus to zoom in numbers. Why, Apple? How about a bit of consistency? So this bill of materials was dynamically generated. Oh look, numbers has screwed up the display because it's converted that to it's removed the leading 0 on the 0603. But if you open this in a text editor, it'll all look fine. This is just numbers doing its interpretation of the CSV. So yeah, we've got a bill of materials, which could then be used for batch.
Now make it export the whole project to better software.
Oh, you can already, well, yeah, you can do that. In fact, if you have a Fusion project and you want to convert it to KiCad, Fusion Extractor will help you.
Cough. KiCad.
Yeah, because this schematic design file is now, as extracted, an Eagle format XML file that can be imported into KiCad. Likewise for the PCB design file. Yeah, so you can individually export those things from Fusion. If you're in Fusion and you're looking at the board view, you can go to the File menu and Export, and then select that you want to export that as an Eagle format XML file, and then you go to the schematic and you do the same thing. So you can achieve the same end result following multiple steps through Fusion, but this just, yeah, Fusion Extractor does it all in one go like that, which is very cool. So that is Fusion Extractor. And some updates to the register. Yeah, designs. And as you saw, it now has type ahead filtering on this. So if I type T, E, S, T, it's narrow, test, O, it's narrowing down the search results. Doot, doot, doot. Yeah. Fun, fun, fun. Where are we? Oh, Vic says, nuts, my headphones fell apart, maybe distracted. Oh, Tinker asked, will there be a link to the test carrier board for Testomatic in the Testomatic design? Yes. I think we're talking about circular references here. Oh, true. John said John's nerd brag. Yeah, okay, that can be my nerd brag. Was publishing a Python library during the week. Grant says, I've spent 40 years working on ERP systems. Non-trivial, yes. Non-trivial is an understatement. So part of what I'm going to be doing, in fact, now that I'm here, let me see. I've got to stop the server, and then I've got to reopen Companion, and let's see if Companion runs. Companion, maybe? Let's shock you for a second. Yes, it works. Okay, let's go away again. So Companion is back running, and I've shut down the local register server because they were both running on 8,000. I could change the port of the... I could change the port of Companion, or I could change the port that register runs on. Alright, so Fusion Extractor. Done on my list. Nerd brag. Done on my list. Yay! Yes, so Grant said ERP, non-trivial. Yes, I agree. Luckily, I am not trying to build a commercial ERP system for general widespread use by many people with differing requirements. I have a little bit of the luxury of being able to make executive decisions about excluding certain functionality or dealing with my own particular use case rather than trying to be super general and support every possible thing. So I'm going to just, I'm going to build what I need. David asked, I'm back in the chat a little bit here. If I have a 3.4 volt stepper motor and I run it with a 12 volt input stepper motor driver, will the universe collapse? No, is the answer. That is really, really common, super common, because the way stepper motors are typically driven is based on power. And with controlling the current to manage the amount of power that they are dissipating, when the voltage goes up. So it is really common. A lot of the time when you look at stepper motors, like NEMA 17 steppers, what's the voltage? The voltage rating on those is only a few volts. It's like 2 something volts. And they're often only a couple of ohms resistance in the windings. NEMA 17, not 16, stepper specs. And operate at 12 to 24 volts. Oh, that is AI lying to us again, kind of. All right, so, well, technically it's AI not understanding what's going on. If you just read the headline, it'll say operate at 12 to 24 volts. Yeah, that's kind of, it's kind of true, but it's kind of a lie because what happens is, my guess is that what's happened here is that whatever LLM is doing this, where is it, Gemini or whatever, is has read through blog posts and tutorials where people run 12 and 24 volt or even higher power supplies running into stepper motor drivers. And so if you simply read this without understanding what's going on, you might think, yeah, you can run it at 12 to 24 volts, no problem. But what's actually going on, phase resistance, yeah, as I said, it's in the order of a few ohms. And rated voltage is, here it says, between 2.7 and 12 volts. Rated voltage might be only a few volts, and yet you run it at 24 volts or 36 volts. And the reason is the stepper motor driver stepper motor drivers are smart enough to manage the current or the amount of energy that goes into them. And so by running with a higher voltage and limiting the current, you can get a similar amount of energy into it in terms of the heat that the system has to dissipate, but you can get more torque. So a stronger electromagnetic field. Yeah, the NEMA 17 steppers that are typically in 3D printers, the ones I've seen are often rated at like 2.7 volts. That is normal. And yet they run on 24 volt power supplies because the stepper motor driver takes care of figuring out one versus the other. So that was a very poor explanation, but okay. Getting closer to my... okay, so SK Photo Guy, Nerd Brag. Finally getting closer to my custom DMX console being finished software-wise. Finally done getting 18 rotary encoders, talking to an ESP32 with the OXRS libraries. Nice! That's cool to hear that you're using OXRS. Yeah. Paul says, I got a closure script program to display photo images in a browser, Chrome-based, for a USB stick. And I had AI help and used all my free tokens and time. Yeah. Okay. Wagonload says, not a nerd brag, I had a chat with AI about how to fix a crashed SSD while being booted from an ISO drive on the crashed computer. Okay. Vic says, I'm now covered in super glue and securely fastened bits of blue tape. And, and Discmaker said, if you do it at a higher voltage, your stepper will be quicker. My CNC homemade is running at 48 volts. Yeah. Crispian asked, how much smoke does a stepper motor contain? Not that much. They do not. A very disappointingly, sadly small amount actually, because if you let the smoke out, what happens is that you get a very small little poof of a short inside the coil or an open as it burns, and it's all contained within a big metal block. The smoke doesn't escape generally, it stays contained. Certainly nothing like the amount of smoke that can be contained within a little resistor or even worse, a capacitor. They can have a very good smoke content. Okay, let us. Stepper drivers on the other hand, says Vic. That is absolutely correct. So a stepper motor doesn't have much smoke in it. If it fails with a dead short across the coil, which can happen if it melts internally, and keep in mind that the coil on a stepper is only in the order of a couple of ohms of resistance anyway. It's almost effectively a short circuit most of the time, like even in normal operation. It is the inductance of the electromagnetic field which gives it more reactance. It's not really a resistive load as such. So talking about the ohms of resistance of the coil is a little bit misleading. And but if you do perchance dead short a stepper, the driver that is trying to drive said stepper may become very, very angry with you, and it may express its displeasure by like a squid expelling a cloud of smoke and then going bye-byes. So what am I doing? I am switching to this, and then I'm going to switch to the overhead. So to remind everybody, access driver for the MRAP Micron, that is the end result of what it looks like once it's fully assembled. We are about to switch to the reality part preparation. We've got that, and that. All the bearing nuts, that's all done. Limit switch wires, I need to attach some limit switch wires and stick, that is done. This is all done, that's together, this is done, that's done, that's done, that's done. Done all of that. That is done. We have assembled the drive thingy here. Oh, I'm going to put some lubricant in that. We've got the structure together there. We've got the loom bands over it. We have the stepper ready to go on. Not actually on, it's sitting beside it. But we are just about at this stage. And then we need to put this part is where we're up to. So let us do this. Do I need to do that? I kind of want to glue that because I don't trust me tensioning them against each other. So here we go. Let's switch over to this view and see the reality of what is going on here. So we've got the Tiny G driver. This is the Pika with nuts in place and things. Oh, a question for Vic. Something that has confused me. I didn't even notice this until this morning because I had not put A and B together and got D, but I now have put A and B together and got D, which is these three screws are holding nuts in place. The nuts are inside this this structure here for screwing down this, which is where the microscope slide goes. We've got the UV LED on the back there for drying the resin. This is the little flexure coupling, got magnets glued in there, but the spacing is wrong. I don't know what I've screwed up here. I've probably got two different versions, like one version of the picker and one version of the stage plate. This gap here is the same as that gap there. You can see that aligns. But this gap, the width, left to right, not that I've got it oriented the correct way, but anyway, left to right, these are closer together than the distance between there and there. So if I put that down like that, they do not align. These ones align with each other. That one can align, but they cannot all align at the same time. So maybe this is out of date. It's a hardware problem. Let me check my code. Oh, okay. Okay. Tensioning works fine. Just do the rotate the lower nut test. If it fails, it'll go then. Okay. Wagonline says, Nerdbreak, I'm working on a project using a quadcopter motor as a gyro flywheel to stabilize a laser aiming system. Oh. Oh, Vic says, Tamara wired an NEMA 17 to an Adafruit driver board with no current limit, not really realizing they had different resistances, and boy did that one go off. Ooh, okay. Yeah, so running with a motor driver board without a current limit. Yeah, very, very bad things can happen in that situation. Yeah, Tamara probably got a shock when that happened. Yeah, okay, so if I unscrew these, now just in the very short term, I may be able to make this work by only screwing one side down, but that seems fraught, to say the least. Perilously fraught. So if I sit this on here, and these holes are aligned with these nuts, like that, I could screw it down there, but it is, as you can see, looking straight down on the camera view, I'm going to point something out. Right here, you see that little gap, you can see a little bit of the edge of the base structure sticking out on that side. You can't see it on this side. That is because this structure is slightly offset to the left, only by like 2 millimeters, maybe even less. If I move it across to the right slightly to get it centered, this hole does not quite reach and these holes do not quite reach. So that is centered, that's about where it should be mounted. But if I screw it down on the left holes, it goes there. So that's just something I need to figure out. I don't think that is going to be a problem for me right now, because what I'm going to do is put the axis driver on this side to be able to move it like this. That's my goal. And then this can be done afterwards, once I've figured out what's going on with this. I could possibly do it by modifying this just by drilling holes, like elongating these with a, I get a reaming tool in here and elongate these holes slightly, and then I could screw it on there. Or I could print another one. All right, so mentioned in passing. Now, where are we up to? So what we need to do is attach this. This is the assembled axis driver, and I thought I had some. I found this a couple of days ago. When I was assembling this, I said that I didn't have any lubricant to put on in between the nuts in here. Sorry, not the nuts. In between the washers. And
Waltep said, "Are we there yet?"
Are we there yet? Yeah, we're there. Railway tap. So, Wagonline says, can you elongate the holes so the upper board is centered? Yeah, possibly. Oh, Vic says, I'll modify the stage. Oh, okay, yep. So there is something odd going on. So in here, you're not going to be able to see at this sort of zoomage, but in here, there are a pair of nuts that are locked onto each other on this bolt. And then there are a pair of washers. Those washers are forming a thrust bearing. because the loom bands are pushing everything in this direction and applying force onto the face of these washers. So that's where we need to lubricate. So if I, with my left hand, if I grab the end of this this M3 bolt and I pull it, I am opening up a tiny little gap just here. So what I'm going to do is open up that gap by pulling on it. Now the washers are separated, and I'm going to put just a teeny tiny drop of lubricant. So this is a very fine oil that is used in like RC cars and those sorts of things. Come on, can I get a drop to come out of the dispenser? Why are you not dispensering a drop? Is there any in there? Maybe this is empty. It feels like there's some in there. Okay, maybe I need to go and yeah, yeah, it's just going shunky shunky. Oh, a drop did come out. There it is. Yeah. I only need a little bit. There we go. But I should get some more lubricant. Alright, so that now, that should spin very smoothly. It feels smooth. Nice. Okay, so now we can do, you can see how much I'm turning the, ooh, I'm going to need more tension on these loom bands. Ooh, I think I'm going to have to insert the spacer to pull more onto this. So if I turn, so I'm turning the bolt clockwise from this point of view, which winds the end this way. I'll try to brace it so that it sits still as I turn it, and you'll see this part move in this direction, down towards my left hand, where the yellow ring is. So as I'm turning it, it's moving towards the left, and if I turn it counterclockwise, it moves back towards the right, and that is how we are moving the stage. But once it gets to this point, look at this. The loom bands are becoming slack. I'm able to push that with my finger, and there is a little gap in here because it's trying to sit in the middle. So I need to apply more pressure to the loom bands by having something under it that tensions it. Luckily, Vic prepared one earlier. Although it seems like it might be a little bit too enthusiastic. Oh well, let's find out. It may be too enthusiastic. Look how thick it is. I think I only need something about half that thickness. So this, the idea is this goes under the loom bands and stacks on top, and it pulls more tension onto them. So I'm going to slacken this right off that way so that this can move. It may end up with too much tension. So I'm going to try, how am I going to do this? I need to do it in such a way that the loom bands do not slip off the other end, so they need some tension held on them. Okay, maybe tweezers, bent tweezers, so I can pull it up and hook that under. Well, what do you know, that actually went far easier than I expected. Let's see if I can screw it up on this side. Pull it up and up. No! Don't come off, don't come off. Pull it up and over. Yay! Okay, so that spacer block is now sitting on top. The loom bands are now tensioned better. And I'll try, yeah, so now it keeps the tension on even as the stage moves up towards that location. But I'm going to go back the other way because my worry is that it's going to end up with too much tension as I come down in this direction, offsetting the axis that way. But no, it seems fine. I can offset it that way without a problem. Okay, I'm going to recenter it. Here we go. Recenter. Now my worry is that if I overdrive this motor driver, okay, this is the axis, like the stepper for it. If I drive this too far, I don't want to damage this. So the first time that I do this, I'm going to be super paranoid. And then this fits into here, and you can see that the head of the bolt goes into this coupling. And once it's screwed down, when the motor turns, it then turns that bolt, which then moves that axis. So I need to bolt this onto here. How do I do that? Okay, looks like... Oh, okay, so the nut is already in there. That's right. I think when I was assembling these, part of the process was to put a nut in so that it is captive on the bottom here. So if I've got a 50mm bolt, like that one, which reminds me that I need to find them. Where did they go? I had that little bag of 50mm bolts. And now I'm wondering if I have enough 50mm bolts. Yeah, so there should be nuts down inside there. So if I put this on here and push it on, like that, push, I should be able to put a 50mm bolt all the way down through here to reach the nut at the bottom and screw this on. And then I need another 50mm bolt for the other side. Ideally more, because I want to put one in there, yeah, two in there. So I need to find where. Now, does this still move? It does. Yay. The stepper can move it. Okay, so I need to find where I put my 50mm bolts. I have a feeling they're on a bag. In a bag, sitting on the pile of drawers with all of the miscellaneous stuff. And they're not. There must be a location where I have other RepRap Micron parts, because I've got the box with the with the 3D printed bits in it. I've got this box named RepRap Micron, and it has a whole lot of things in it. It's got 3D printed parts and some nichrome wire and microscope slides, other supplies that I need for doing this project, but it does not have several things that I was looking for earlier, including the 50mm bolts. So, where did the 50mm bolts go? That is the question.
Where did you store the 4D printed parts?
Yeah, the 4D printed parts. Well, 4D printed parts are really, they're great for storing because they don't have to take up any space in your current timeline. You can just put them into a different time location and pull them back at will. So a 4D storage system is fantastic. Oh, what is that? No. What did I do with my 50mm? Yeah, he stored them in the future. Said Crispian.
He stores them in the future.
That's it. Ooh, I just had a glance across at Castnote again. So, g'day to Paul Schultz, Jisk Maker, Dodgy Brothers, Mr. Fixit, Don S from NZ. Welcome to the whatever this is. I am not entirely sure at this point in time. Okay, I am going to do something dodgy now. I'm going to try hooking up this axis driver without additional bolts. And everybody's going to be screaming at me saying, no! Okay, this side of the axis driver. Oh, I wonder if... Did I put them in the drawer? M3... Okay, you can all laugh at me now. You can laugh at me. You know where these M3 50mm bolts were? They were in this drawer that says M3 50mm. Did I think of looking there? No. Is my brain defective? It is most assuredly so. Magic 8 Ball says yes. Okay, screw these on. I think I may actually not have. Yeah, no. Do I? No, I actually don't have enough 50mm bolts for all 3 axes. Not if I put 4 bolts into every one of them. Because when I was ordering these bolts, I think I ordered a 10-pack. And that was on the basis that they came in 10 packs. And so that is just turning now. Isn't that biting into the nut? Don't know what's going on with that. That is on the basis they came in 10 packs. And in my head, I thought that I needed 3 of them because I needed them for the long driver thingy for each of the axes. Yeah, I thought that's going into the nut in the bottom, but maybe there is no nut in the bottom. I don't know. It seems to be held on though. Okay, so I've got 4 bolts holding that that stepper onto the stage. The stage is now aligned. In fact, I will go which way? That way. Turn it that way. It's now dead centered, aligned.
Pro tip, minimum order must always be at least double of requirements.
Well, yes. So if you couldn't hear that, Tinker says, pro tip, minimum order must always be at least double of requirements. That's what I thought I was doing, because I thought that I needed 3 M3 50mm bolts for that, and so I ordered 10, thinking that I would have spares. But I didn't account for the fact that you need 4 more for every axis driver for bolting that part of it together. Don't know why I didn't notice that, but that's the way it is. Okay, I can get around that. That's not a huge problem. So what are we going to do now? What we will do next is, let's make this move in isolation from the which way? In isolation from the stage first. So that, yeah, I'm trying to get my head around how all of this hangs together still. I don't entirely get it. So, because my brain is not as big as Vic's.
John Dashwood said, pro tip, the number required is always twice as many as thought.
Yep. You always need more. Okay. Axis driver. I'm going to stick this one into channel 2. 1, 2, 3, 4. Yeah, I'm pretty sure it goes right to left. So, what do I need? I need a...
At Paul_Schultz said, can you just match his to the base?
Can I just... who now? Match. Can you just match this to the base? I don't know what that means. Okay, match? Oh, do you mean attach? Are the motor mounts color-coded, says Wagon Loads. Kinda. I have not yet assigned which color goes on which axis. All I did was print them in 4 different colors so that later, once it's all assembled, it'll be very easy to see what the sub-assemblies are. Glue is not your friend? No. I don't want to glue it. I don't think I need to. Okay, so, yeah. All right, good. That is on. This one is the other one that we were using for testing. In fact, what I'm going to do is use this, because it is untethered, to drive it before I drive this one, which is tethered to the structure, so that I can see how fast and how far this one turns based on the commands that I send it, before I do the same on the second channel. I think that is going to be a very good little safety thingy. So I need voltage onto there, and I need USB onto there, and then we can talk to it and we can make the axis move, which is kind of a big deal. Kind of a milestone. And then I can attach it to the Pika. What's the time? 11:39. Okay, yeah, I can attach it to the Pika. And I still I can't even visualize how it attaches to the Pika. So I do want to do this while Vic is ready to shout at me and tell me what I should be doing. I need power supply. Which means I need...
Found the modeling bug. Kicked myself. Fixed it on GitHub and printables.
Oh, okay. Awesome. Thanks, Vic. So, if you couldn't hear that, Vic just said he's found the bug in the model for the pattern, the bolt pattern on there. So, yeah, I will figure that. I will test that out. Check it out. Not now, though. That is for another day. For now, I am going to try this. So what have we got? Power supply. I need lab power supply on. I'm going to give it about 12 of the volts, I believe. Oh, 13, close enough. It's set to 13. All right, so we have motor 1, motor 2, and I believe the way this is mapped in the TinyG firmware right now is that's the x-axis, that's the y-axis. But of course, all of that is remappable and we can reconnect things. But for our purposes of simply driving this and making it move, Vic says the bug was in Pika sheet 2 and you only need a new stage. Nice. Oh yeah, and Paul is also in the process of doing this. Right now you can't see me, haha. So I'm going to bring up, oh damn, now you can see me. I'm going to bring up cool term. And up here, cool term options. We want that one, we want 115, 200, terminal will stick in line mode, and we will connect, and then let's see what config we've got loaded.
Said, hangry o'clock here, bye.
Bye, Pete. Bye. Go and be hangry. Okay. Seriously though, Pete, thanks for coming along. Where are we? Okay, I am on motor 1 maps to axis is X, motor 2 maps to axis is Y. We've got 0.9 degree steppers set for both. The M1 travel per revolution is going to become important. In fact, let's have a quick look at Vic's settings here. So these are gerbil settings for for his motor setup. Homing locate feed rate, millimeters per minute. 5,000. You've got masks on here. Hard limits enable, homing cycle. What I need to do is take some of these and translate them into the equivalent TinyG config. So, x-axis travel resolution, y-axis travel resolution, steps per millimeter. There's a little bit of tuning in there. It looks like 33.642 on the y-axis. So if I set the, what have we got? Y-axis maximum rate, millimeters per minute, acceleration, x-axis maximum travel in millimeters. Okay, so where is the setting in here for travel resolution steps per millimeter? Okay, I need to figure out the equivalent as settings that I put into here, because I believe the way TinyG does this is slightly different. You can see here, for example, it's a 0.9 degree step angle, and it is travel per revolution. And what I need to do is figure out the equivalent of, in that set of units, of the x-axis travel resolution in steps per millimeter, which is a compound of the step angle and the travel per revolution. So, steps x-axis travel resolution steps per millimeter. Jisk said, isn't a step or angle not normal 1.8 degrees? Yes, not the common ones, yes. But these are 400 count steppers. So a standard stepper, if you just buy like a bog standard NEMA 17 stepper motor, they are 200 pulses per, or 200 steps per revolution, which gives you 1.8 degrees resolution per step, like 1.8 degrees of rotational resolution. But these are 400 step per revolution steppers, which gives you 0.9 degrees of resolution. And that is necessary in order to achieve the very fine movement that is required to set the position on the RepRap micron. You can use 1.8 degree steppers, but you won't get the resolution that Vic is getting. Jisk says you can get 0.9 degrees. Yeah. Yes. Exactly. And then we run micro steps below that as well to get even finer resolution. So yeah, I'd already reconfigured these for 0.9 degree. You can see that the driver on motor 4 is still set to 1.8 degrees. So yeah, RepRap Micron is really pushing the limits of what you can achieve. Paul. Okay, so Paul has a question for Vic. You two can chat among yourselves. Okay, what am I doing? Travel per revolution, 1.25 millimeters. Okay, I'm not sure if my brain is up to figuring this out live in front of people while you are watching me and laughing. Let's try getting the robots to figure it out. So I'm going to say convert. What am I looking for here? 32 steps per millimeter stepper resolution to what am I looking for? Millimeters travel per revolution. Okay. Total steps per revolution. Travel is 100. So that is, identify your motor's steps per revolution. So that is going to be 400. So here we go. It is 400, oh, by micro stepping. So what micro stepping are we running? Micro steps, we are running 8 micro steps. Surely you don't need, calculate travel per revolution. Yeah, that's what we want. Full stepping, yeah, 6.25. What's the setting there? 32. I'm not sure this is going to be correct, but I just want to make the axis move a little. The main reason I'm trying to figure this out right now is I do not want to make the axis move too far and break it. I want to make sure that my movement is bounded to the safe range right in the middle of the mechanism, so it's not stressed. Okay, 6.25 millimeters per revolution. So M1 travel per revolution, steps per millimeter, 31 steps per millimeter. Stepper motor, steps per millimeter, calculator. Okay, oh, there's a calculator. No, I do not want you to know my location. I went to the steps per, the Fergelli automation steps per millimeter calculator, and it wants to know my location. No, okay, so I am going to do, in fact, let's, I'm going to bring this up on here. So steps per revolution, 400. Yes. Now micro stepping, we are running 8 micro steps. Donk, donk. Lead screw direct drive. Yes.
I reckon 1 micro step was about a micron, so set steps per millimeter to 1.
Oh, okay. Where is it? 1 microstep was about a micron, so set steps per millimeter to 1. Okay. Lead millimeters per revolution. Distance travel per complete motor revolution. That is, surely that's what we're trying to calculate? No, distance travel per complete motor. All right, let's just try 2 and see what this calculator gives us. Steps per millimeter, 1,600. Resolution millimeters per step, 0.000, all the O's, 625 millimeters. I'm going to ignore that and go with Vic's suggestion. So on motor 1, travel per revolution. So I want to set 1 TR. I was set to 1.25 currently. So it was already close to Vic's suggestion. So I'm going to do 1 TR equals 1. And I'm going to do 2 TR equals 1. Yeah, distance for 1 rotation equals thread space. Yes, that's right. It says wagon loads. 1 microstep. So, yeah, so that's the pitch on an M3 thread. Wouldn't millimeters per revolution just be the thread pitch of that bolt? Yes, Tinker, absolutely. Paul says, oh, okay, what's this in relation to? Paul says, wishing everyone who has to deal with it a very happy, merry, good 6-7 day. Okay. I don't know what that's in reference to, but okay. Now, I am going to do a very small movement here. I'm going to say G0 X. So the first motor, which is the one that's not connected to anything, is X, and I'm going to move it to 1. So 1 millimeter of movement, which according to this, we now have travel per revolution 1 millimeter. This should move it 1 rotation. So let's see what happens. And in fact, I'm going to put a big fat Sharpie marker on this. So I've got that queued up, ready to go. Let's switch to the other view. I'm going to put a Sharpie marker down here. so that you can see it easily. I'm going to rotate this so that it is directly facing me. So this is the marker. When I run this command, this stepper should turn, I don't know which direction, it should turn 1 revolution. I hope. It may not, it may not. Let's see what happens. And, oh, it did it. 1 revolution. Perfect, okay. So 1 millimeter per revolution. So that, but the pitch, okay. So the pitch of an M3 bolt is what we should have as our travel. Oh, and also, where are we? I'm just trying to read back in the chat. Vic was saying something earlier. So set steps for revolution to 1, and then there was a, oh, there, okay, so Vic says there's about a 2.7 to 1 mechanical advantage in the flexures. Yes. Replying to wagon loads. Yeah, okay. All right. Let's try this. I am going to move that axis by 1 revolution. I'm going to sit this in, hopefully in a way where it's, I'm going to use this other stepper as a stand. There we go. It can sit like this, maybe. And then I'm going to move this stepper, and I'm going to put the Sharpie marker down here. Oop. Nope, don't want it to fall. It's got to be stable. So I'm going to move this axis driver by 1 millimeter. It's going to go that way, unless the motor has been reversed, because you can set that in the config. It's going to go that way, which is going to wind that way, which is going to move the axis in that direction. All right, so I'm going to move y-axis 1 millimeter. Here we go, first ever movement. Oh, look at that. Look at that. 1 revolution. Okay, I've got to, it hardly moved the axis. It's, all right, now I'm going to move it to 2. Yeah, it's moving it down this way. All right, now I'll move it back to, I'm going to move it to -2, which moves it up that way. So it's going to move a total of 4 millimeters this time when I hit enter. It's going to rotate 4 times, move it that way. And you can see that this stepper is running much more slowly. The settings on this stepper are different. So it is moving the axis in that direction. You would not even be able to see that. I can barely see it. Like, I can just see with my eye that it has moved this way by a very small distance. This is awesome. So I'm going to 0 it. I'm going to move that axis back to the center position. So it's pulling it back down this way again. And now we have this axis back on its center position. Groovy. Okay, so the next logical thing to do is to put the limit switch on here so that this can home by itself. At the moment, I just rotated it until it was in the central position when I bolted it together, and everything is relative to that. But we can put the homing switch in place now. And I've got the wire for making the homing mechanism, which gets clamped through here and bent over and then bolts onto there. That way? That way, I can't remember. It's in Vic's fine instructions. So now, yeah, I can make the homing switch for that axis. But before I do that, I want to check how it attaches onto the picker, because this bit I have not yet got my brain around. Let's move this out of the way. So the driver board is up there out of sight. Move that out of the way. Move the picker into place. So, how does that attach to that? This is the mystery. I believe it is through these things here. So, look at this. If I put this, you can see that there are these nuts on here, and there is this structure here. Yep, got to put all this down very carefully so I don't break anything. Okay, now this structure here, if I push this in and out, it moves the base that way. So what is happening is this goes on. So yeah, Vic, shout at me if I'm wrong about this, but I think this is what's going on here. This goes on there. Is that it? Oops, I'm just knocking other things. No, which way? That way. I had it upside, no. Did I have it upside down? No. What is going on here? How does this go on? I am totally confused. Okay, I'm going to look at the instructions because I need to figure out how this fits. Okay. Oh, Vic says, with the distances moving, the best bet is to count 3D printed layer lines through a microscope. Yeah, okay. Yeah, they are tiny. My son is too old for this. Oh, okay.
No, not the instructions.
No, not the instructions. The L shape wraps around the corner. Oh, okay. Huh. Oh, there. Okay. Hang on. Let's switch back to here. So this goes there, I think, sits in there, that goes in there, that slides in. Oh, look at that. That is a thing of beauty. Okay, so now bolts can go in from there into there. And I've just got to make sure. Okay, so before I do that, I need to put nuts into these locations. On the yes, on the back here, I'll put this down carefully. I need to drop nuts into those 4 locations so that bolts can go through there. Oh, do I need the top ones? Where do those bolts come from? I'm not sure. All right, I'm going to put nuts in here. I think we're about to have the actual stage move.
Just the 2 lower nuts is okay.
Yep, okay, just the 2 lower nuts, yes. So, oh, also, just a little tip. One thing for people who are building this, so Paul is definitely building this, he's probably already figured this out. Nuts are hexagonal. The design of the slots here is for 2 parallel sides to go vertically, in this case, into the slot. If it rotates so that there is a flat top and a flat bottom, the nut becomes wider and it doesn't fit properly. So it has to go in with the 2 sides parallel, but if you put it in like this, so say I get it started into the hole, and then I get myself a flat screwdriver. This is the obvious thing, to push it in, and you put it on the nut and you push it. What happens is the nut will rotate because it tries to put a flat face on the top where you're pushing with the screwdriver, and it can all go very badly wrong. So a tip for anybody else that's doing this, I found the best way to do this is with
a nut insertion tool. It is in the utils directory.
Oh, nice. Thanks, Vic. So Vic has made a nut insertion tool. But what I found works well is something like needle nose pliers, and you put them on just slightly apart so that the tip is apart and the corner of the nut sits in the middle. So what that does is it applies force on both sides. You're not going to be able to see this because of camera angle, and it goes in and it doesn't rotate because it's applying the force on the two sides of the nut and keeping it aligned. So it goes down straight without rotating. So I'll do the same on this side, push it straight in, and I think that is done. I'll just make sure they are fully bedded down, and now I should hopefully be able to bolt that on. I wonder if, okay, I'm going to try putting that through the nut. Oh, that doesn't go in far enough. As a test, let's grab that and screw this into the nut. Where, there. And see if it'll go in. Nope, looks like I haven't got it fully in. So here I am, giving a tip on how to insert nuts and failing to insert nuts. Nope, it hasn't quite bedded down into place. Maybe I do need Vic's nut insertion tool to do this properly. Oh, that one, I just heard a click. Yeah, so now they should be fully bedded in. Did I take it too far this time? Oh, I did slightly on the one on the left. I think the one on the right will be okay. Maybe? Maybe? I want to get this going in before I try to do it in place, because then it will be harder. Yeah, so that one is going in. That is good. So this one, I will recenter the nut with that. And now let's see if it will go in. I've got to look down. Next size screwdriver, that one. See if that will recenter it. Try again. Because if I can't get the bolt in here, oh, that's it, that's perfect. If I can't get the bolt in here where it's just sitting loose on the bench, there is no way I'm going to get the bolt in when it's in the mechanism and trying to go through the structure here. What length are these bolts? I hope they're long enough. I hope. Okay, so I also need to get it into that one and that one. All right, I need a nut in there. So I will insert a nut into this slot before putting the rest of it together. That one just fell in. Then, here we go. Attaching the driver. So, Vic, I'm curious. The driver that sits in this position, which one is this? What axis do you call this? This would be the x-axis, I think. If this is the orientation with the... No, the microscope isn't normally to the front there, is it? What is the front face? So if this is the orientation, then this will be the x-axis because it's moving left to right. But I don't think that is necessarily the case. Now, how do I tighten up these bolts? Oh, ideally I would use bolts with little hex heads so that I could tighten them up. But I'll see if I can get the hex driver onto it. Oh yeah, that goes on. Screw that on. So we are about to have the very first axis driver attached. Now I've got to put a couple of bolts through there. What length do I need? Are these too long? No, they're perfect. Very good. So that one can go into here.
The side with the microscope clamp points at you.
Okay, so this is the front. which means this is the x-axis driver because it's moving that way. All right, that one on, and then one more. And then this axis driver will be fixed. Is it going in? Yeah. Getting there. All right. So that axis driver is now fixed in place, but it is not yet attached here. That needs to be coupled to this so that it can move the plate this plate sideways. Now I'm going to move the whole thing and stand it on its edge so that we can look straight down on the side of it, and it needs to be bolted through here. So there are two little bolts to put in. What'll I use? I could use these. These are 16s. They're probably a little bit too long. Probably looks like about 10s would do the job. Should have some, oh, maybe a 12. I'll grab a couple of.
Swivel hex heads allow around 20 degrees off axis.
Yeah, swivel hex head drivers are nice. So I'm going to put 10, yeah. I'm using 12mm here. They're going to be slightly too long. I'm going to grab 10mm instead. Swap out 12s for 10s. Put 10mm into this. Yeah, nice. And a 10mm into this. There we go.
12 is fine, 10 is best.
Yep, okay. Thanks, Vic. I assume it was Vic who said that. Yes. 12 is fine, 10 is best. These are 10s that are in there now. Okay. I've been hesitant to do this because of the risk of taking support away from this central point, but I think it is now time to bolt this spacer back in place. It goes on here, and this is going to need what size? Will a 10 reach? Yes, I think it will. A 10 or a 12 will do this. What did I had it in my hand right then. I have lost something. Oh, there it is. The hex driver. No, actually, maybe 10 isn't long enough. Is it going to reach? Might need to be yeah, it needs to be a 12 or a 14 to get, or maybe even a 16 to get into that. Let's go for a 16. Grab out the 16s, because that'll put it right about there. Yeah, that's good. 16s are fine. Could get away with a 14. What this is going to do...
Turning off disconnecting the driver would simplify life. I think I needed 15.
Yep. Yeah, 15. So I'm using 16s at the moment. Oh, I should have done this before putting that axis driver on. That's okay. I can still get access to one of the bolts on this side. I could take the axis driver back off to to put the other bolt into this corner, but I think it's going to be fine. It doesn't really need both bolts in that corner. Right, I'll do this one up. Going to be very strongly attached anyway, and it's only a spacer. This base part just holds the structure up off the bench and allows the central plate to move easily. Okay, so a little bit of an update on other things while I'm doing this. Last week, I talked about...
She'll be right, mate.
Yep, she'll be right. I talked about security systems, and Gav decided it was his mission in life to hook me up. So I'm expecting him to turn up here anytime. He he was planning to come over at the end of the stream today, and he's bringing me an alarm panel, a serial interface, like an RS-232 interface module for the alarm panel, and a keypad and cable and a bunch of other things. And the particular panel that he has chosen for me, it's from a New Zealand supplier, and it is very automation friendly. They've got a serial interface on it, and they publish. Ooh, okay, I will stop talking. Yeah, what am I doing? Okay, we're at the stage where we can make this axis move. However, I'm going to do this under a microscope. Let's scope this up. What do I need? I need power on the microscope camera. I need power on the HDMI.
So next week's stream will be all about John trying to get back into the lab without setting off the alarm.
Maybe. Okay, I've got to do a bit of rearrangement here so that I can get this microscope up above the stage plate. Well, it's not really the stage plate, it's the... Yeah, I'm going to switch to the microscope view in a minute. In the meantime, I am just making a mess here and trying not to have everything fall over. In fact, I'm going to rotate this backwards, okay? But this is only because of the way all of the cables are laying out on my bench. So, how do we get some focus on this microscope now? Let's see what I will see if I can get it down to a point where it's focused. There, approximately. Yeah, approximately, something like that. Oh yeah, that's okay. Now, I'm going to switch to microscope view, and then I'm going to fix some focus. All right, what we're looking at here is the top of the stage plate, and because it was hard to focus, I just chucked that connector on top of it so I could see where I was looking, and then I'm going to take it off. So these are the lines. They're not actually layer lines, they are extrusion lines on the top of the structure, that center structure in the RepRap micron. And so, and you can see there is something, I'll see if I can use tweezers. Oh, it is so small that I've got to find it in real life. Okay, somewhere there, you see that little dark dot right there? That is a very, very small speck of dust. I actually can't see that with my eyes. Even well lit under the microscope, in that area, yeah, where the microscope is, I cannot see that dot with my naked eye. But that is going to be our reference. In fact, I'm going to try moving the entire thing, which way? That way. Okay, well, we've got two dots there now. So I've just moved it like a fraction of a millimeter on the bench. Let's get see if I can get some better focus. I think that's about as good as it's going to get. All right, now if I move the y-axis driver in, all right, I'll show you what I'm going to do. What I'm going to do is move. So the y-axis output on the TinyG is currently running.
There will be some wobble because it is not stabilized by the y-axis.
Ah, okay, cool. Yeah, so there are the two drivers, like one moves one direction, one moves the other, and because they are both attached to that center point, one of them locks it in one axis, the other locks it in the other. But if one of them is not even there and you try moving it, it's going to wobble because the other axis is not stabilizing it. So what I'm going to do is move it from the center point to 2. So I'm going to hit enter on that, but I'm going to, see the wobble that's in that? That's me touching the workbench, like over near my keyboard, just touching it. All right, I'm going to be very still and press enter, and let's see what happens. This could be a historic moment of the very first time this RepRap Micron moves one of its axes. So let's see what happens when I press this. Oh, look at it go! Look at it! It's moving! Oh, that is so cool! Okay, now I'm going to do the opposite. I'm going to go, this is going to be a bigger movement. So we went from 0, so centered, to 2 millimeters. Now we are going to go from 2 millimeters to minus 2 millimeters. So this is going to be a 4 millimeter movement when I say 4 millimeters, 4 from the point of view of the stepper driver, which is then reduced by the thread on the drive nut, and then it is reduced by the trapezoidal thingy, and yes, all of that. So I'm going to tell it to move 4 millimeters.
Said, and hardly any wobble.
Yeah. I'm going to tell it to move 4 millimeters, and we will see it do its thing. So 3, 2, 1, go. Look at it move. Oh, this is amazing. Okay, there we go. Oh, Gav says, a tad late. a tad late to the stream or a tad late to the lab? Okay, I'm going to try moving now. I'm not quite sure what I can achieve out of this. So it was at -2. I'm going to make it go to minus...
Brad Meisel said, but the pitch of M3 screws is 0.5 millimeters, so less before mechanical advantage.
Oh, okay. Yes. And also the 80-to-1 reduction or whatever it is in the trapezoidal axis driver. There are all of these reduction factors involved here. There are, in order to get the superfine resolution of being able to move those little dots by microns. Oh, flat tire issue, says Gav. Oh, okay. So where are you now, Gav? Do you have an ETA on when you'll be here? So I'm going to switch back to this. Okay, so I'm going from 2 to 1.8 millimeters. So this is going to be a 0.2 millimeter movement according to the stepper driver. And let's see how much those little dots move. Ooh, a tiny amount. Such a tiny amount. Yeah, Crispian says, oh, maybe TTS will do it. Let's see. I hope so.
Careful with your units. Don't leave out one of the mis and have it try to go 1,000 millimeters.
Yeah. Yeah, that's right. I do not want to be overdriving this. Okay, I'm going to... Oh, Prestonia Northland. Oh, okay, you're way over the other side of town. You'll be ages. Okay. Then, Gav, do you want to do it another day? Because I was going to finish up here and leave. I'm not going to be here for the rest of the day. One small 1/8 step for mankind. Okay, how do we do a 1/8 step? Yeah, I wasn't planning to be here this afternoon other than at the end of the stream. So Gav has security gear to drop off to me. What does it take to what does it take to move 1/8 of a step? I've never actually stopped to think about that. Moving one step, I've got to give it a millimeter distance. So to move one step, it is 400 steps per... Okay, this is going to be really, really small. Where's the calculator? It is currently set to 400 steps per millimeter. Oh yeah, you won't see it through that microscope. Yeah, likely. So, but I'm going to do it anyway. So we've got 400 steps per millimeter, and we have 8 microsteps per step. So by that, so it is 3,200. So it is 1 divided by 3,200 of a millimeter, which is 0.0003125. So let's, just to avoid me having to do any more brain math, because that is unfortunate, I'm going to move this to 0, and I'm going to do it while we're watching it, just for the fun of it. And then I'm going to zoom the microscope in, because this is actually zoomed out at the moment. Let's zoom in, and then I'm going to have to adjust the focus. Bring it down here. I'm going to move it. Oh, try to get those little dots centered. And I think I need... Oh, come on. Okay. Can I go any brighter on this light? Where's the brightness control? Oh, around the back. I can go darker. No, that is as bright as it gets. How about some supplementary light? What can I use as bright supplementary light? Let's try... I'm going to try... This is probably not going to do as much as I want. Try the torch from my phone. It barely adds a thing. Oh, it changes the shadow. I need a much brighter light. Okay, I know what I can get. I have a very bright work light, which I can grab and bring in. Even this may not be enough. Oof, no, I just blinded myself. I think this will help. Okay, I'm going to put, I have this Ryobi battery work lamp. I'm going to aim that at this. There we go. Oh, all the shadows have gone away. And now, can I get the focus just a little bit better? I'm trying to be really still as I'm touching the controls of the microscope here, but it's kind of bouncing around. Okay, now let's move that by 0.1 of a millimeter. So I'm going to say 0.1. I'll be very still. Oh, it moved and I could see it. And now I'm going to move it back to 0. See, it just moved to the right a little bit. Okay, now, yeah, we're definitely not going to see it with this microscope by the time we get to 1 microstep. So 0.01, we are now going down 1 more order of magnitude. Oh, there it went. And now back to 0. I could just barely see it on the microscope. So I'm going to be really still now, and it should jump to the right just a little bit. Barely. And then 0 it again. Yeah, we're not going to be able to tell on this microscope. So that was moving by, yeah, we can go another order of magnitude below this in terms of control. I'm going to go to 0.001. There we go, and then 0. We can't even see it moving on the microscope. It just went then, and then back, and then moved. Yeah, so we've got movement which is exceeding the ability of this microscope to show it. Okay. That is kind of wild. Jisk says, use RGB light, then you have different colors to play with too. Oh, Wagon Load says glitter. Oh, and Jiskmaker said put the limit switches on first just to be safe. Yeah. Yeah. John
And
says.
John Dashwib said, so what microscope do I need to get now?
Wouldn't that be the opposite of exceeding? Yes, you're right, Tinker. Sorry, that was about the comment of exceeding the resolution of the microscope. No, it is below the resolution of the microscope. Below our ability to perceive the movement through the microscope. Yeah, some things are better to see with another color of light. Yeah, so being able to adjust the color would be potentially very useful, as Jiskmaker pointed out. And John asked, what microscope do I need to get now? All right, so another step is that I have, ta-da, this is one of the microscopes that Vic has got on his machine. And I have, this rod is too short to mount it on the frame, but Grant very kindly brought over some for me. And then we've got the stand. So this could be, which one? This could be the microscope that comes directly down from above, I guess. Because this Vic's design is intended to have two microscopes. One for the, one that comes in at a 45-degree angle, looking down onto the print area, and another one vertical looking straight down onto it. So what I can do is mount this one to be vertical directly above the build plate, and then we can get a view through this.
Electron microscope.
Yeah. It's kind of into that sort of scale, isn't it? All right, I'm going to move this away from the microscope so I've got access to the, yeah, this microscope may actually show us more than the stereo microscope that we're using right now, than this microscope. So I'm going to switch to the bench view and move this over here. And the idea with this is, if I'm careful about moving that, all right, there. The idea with this is, this microscope mounts, there's a rod that goes in here, it also goes through here, and this microscope mounts there, looking straight down onto the build platform. So, I need to get the rod that Grant brought me, which is over here. It needs to be cut. So Grant brought me a length of the necessary size rod for mounting this microscope. So what I'll do is I'll put this in, and then I'll figure out how long it needs to be so I can cut it off. But I will do that by putting the microscope on here, like that. It just slides up and down. So I'll do that up for now. And this has a vertical fine adjustment for and there's a adjustment there as well. Okay, let's stick this in. Over to here. This rod is annoyingly long, but I will put this in and then get the distance correct, allowing for the fact that there is going to be some more space above this. Move this down and I'm going to plug this into my computer and see if we can get a view through this microscope and then move the stage again. That would be cool. Okay, microscope is plugged in. Let's get, what do I use? I'm going to use QuickTime Player just to be able to move that off there. Capture, new movie recording, and I'm going to capture off digital microscope. Here we go. Ooh, it's all orange. Okay, so that is the view right now out of that microscope, looking at the center of the bed. So I'm going to move it up and down until we can get some focus. And
Hope you don't inst this one's abilities too.
I might have to take the illumination ring off it because it gets very close. Very, very close. Yeah. Oh, I think those might be the dots we were looking at previously. All right, I'm going to go down even further. I'm going to see how close we can get with this. This microscope is now directly over the over that stage. I'm just messing with the focus on the microscope now. All right. It's actually almost touching the stage. So this would not be practical to run like this.
The illumination ring does not easily come off unless you use a Dremel.
Oh, okay. But I assume that you have taken yours off, Vic. Is that right? Okay, focus adjustment there. And there we go. So now we are looking through the USB microscope. Oh,
No,
left it on.
Left it on.
Okay. So you must have yours raised up a bit and not right in close, zoomed in massively. Yeah, so what we're going to be able to see now is the view there plus, not that one, not that one. I want cool term. So let's go cool term. All right, this is better. Now you are going to be able to see the commands and the movement at the same time. So let's go, we'll zero it just to make sure it's zeroed. And then I'm going to go to 1 millimeter and let's see how far it moves. Look, you can see it moving to the left. And now back to 0 millimeters to center it. Now it's moving to the right. And is there a brightness control on this? Yes, there is. Where is? I'm just going to mess around with brightness control on the microscope. Oh, it's doing auto iris stuff. Yeah, that looks alright. We can see the layers of the. What are they? Are these 0.2 millimeter lines or 0.4 millimeter lines? Whatever they are. This is where the head of the 3D printer dragged along, where the extrusion. So this was with a 0.4 millimeter nozzle. I think you can see that they alternate just because it was one set and then another set. But I think that the average, see these lines that are going diagonally through here? I think that these are 0.4 millimeters apart. I could be wrong. Let's chuck something under there that's a known size. And yes, I know I don't have a calibration slide. That's what I really should have. I'm going to move this. Oh, it's upside down. Interesting. Okay, so this is. Oh, and it's also rotated at a funny angle just because it's coming in that way. Okay, I can rotate the microscope to correct for that. In fact, I should. Let's rotate the microscope around that way so that that is square. It should be like that. Okay, so it's now, the microscope is now squared up. So those are 1 millimeter increments on the ruler. So that is, oh, and I should fix that focus a little bit now because I messed it up. It's focused on the ruler, not on the surface. I'll get it in between. Okay, so now both the ruler and the dot are in focus. You can see that little speck on the surface. So these are 1 millimeter intervals on the ruler. So that's 5 millimeters from there to there. And let's, what are we at? Are we zeroed? Yes, we are. So let's do a 1. Now we can see that that dot is just off the right-hand edge of this mark. So I'm going to move 1 millimeter according to the thing. Oh, of course the ruler moves with it. Let's go back to 0 because the ruler is just sitting on the bed. But you can see in this view the edge of this mark moved just to the edge of the window, and I'll move it back to 0, and then it moves back there, and then just past the edge of the window. So the width of one of these millimeter markers is about the distance that it moves with 1 millimeter of movement in here. Yeah. Tinker said, where's that tiny chessboard I mailed you? Could put Dagnabbit Rabbit in the middle of the platform. Oh. Where is that test board? I'm not sure.
Tinker001 said, John, where's the tiny test board I mailed? You could put Dagnabbit Rabbit in the middle of the platform.
Yeah, I think it'd be way too big. You wouldn't see it. You'd only see part of it. I think it may be stuck to the wall over... Where is it? Oh, yeah, Tinker. I'm not sure, actually, where the stuff is that you sent me. And I would not have a hope of finding it anytime quickly on my bench or around here right now. Sorry. Yeah, okay. This is... I just want to keep doing this for a bit because this is kind of bonkers. Being able to move the platform like this. And let's go 0.2. Look at that. We can move it. 0.2. How about 0.1? There we go. 0.1. 0.1. This is fun. So, I don't know how much that would actually be moving now. So I'm driving it, according to the software, I'm driving it at 0.1 of a millimeter of movement, but the actual movement is way less than 0.1 of a millimeter. Tech Nebula says, I've not seen proof of life for a while. Oh yeah, we can see Steve's fur up close. Yeah, there isn't room in between. So that microscope is maybe, the bottom of the light ring is maybe 3 or 4 millimeters away from the surface of what you are seeing right now. The microscope is right down close to it. So I can't get anything else in there. The ruler that you can see is slid just under the edge of the ring of the microscope. There is no working distance at all. Yeah, so what mechanical magnification do we have here? So if this is, it thinks it's moving 0.1 of a millimeter, according to the software. It's moving way less than 0.1 of a millimeter. It's got to be. Or is it? Yes. Okay, let's do a movement of 1 millimeter. So we're at 0 now. Let's move 1 millimeter. According to the thing. And that moved approximately the width of the track. I wonder how wide those tracks are. I could find that out. Oh, Paul says, is that fully zoomed? Can you screw focus to the other end? It is zoomed way in, yes. I could screw focus to the other end and raise the whole thing up. And the resolution would, like the magnification would decrease. Seems, Crispian says, it seems to go about 0.15 millimeters. Yeah. Yeah, I wonder how wide these are. I have the design files for this ruler somewhere. I could look it up.
At Grant Meisel said, I put a ruler on my screen. 1 millimeter move was 12 millimeters on my monitor.
Yeah. That's very helpful, Grant. Thanks.
At Tinker001
yeah.
said, held up a ruler to my screen. 1 millimeter move is pretty close to 1 centimeter on my screen.
Grant and Tinker, you both did the exact same experiment. Yeah.
See what it takes to move one actual millimeter.
Okay, let's see what it takes to move 1 actual millimeter. So to do that, now let's zero this. It is zeroed already. I am going to move my window to align with, okay, no, what I need is 2 of these that are the same thickness. Oop, that's not what I wanted. I'm going to use that one and that one because I'm not going to do center to center, I'm going to do edge to edge. So what I'll do is put this here so that the edge of my window here is just touching this edge of that millimeter marker. Now if I go to 1 millimeter, it's going to, oh, wrong way, okay. Let's go back to 0. It looks like it's about 10 to 1 to me. Okay, so now if I go to -1, I want to see how far I've got to move it before I touch the edge of the next millimeter marker. So that was -1. Let's go to -7. And getting there. It's going very slowly at the moment. Ooh. Oh, no. That is going to go way too far. I wonder if this is going to stress it too much. I should have gone to -0.7. Or is it? No, -5. Let's go to back to -5. 26-inch screen here. Okay, -4.5. Let's see where that gets us to. -4.6. Yeah, so 4.6, no, 4.7 I think will be slightly overshot. Yeah, 4.64, let's go with that. Yeah, so 4.64, I'm going to write this down so that it's science. Minus 4.64 gets us 1 millimeter of actual movement.
It should survive 8 millimeters of movement.
Okay, cool. So that's 8 millimeters of movement total, limit to limit, 4 millimeters from the center. At the moment, I have 0, so if I do this and 0 it, I manually screwed the thing so that it was 0'd when I screwed the stepper on. So 0 on the stepper, and if it's powered up in that position, of course, 0 on the stepper, so it's now moving to 0, is the center of movement of the x-axis. And then it could go 4 millimeters one way from that or 4 millimeters the other way from that. So 8 millimeters of total movement. There we go. So that was 1 millimeter of movement on that axis. And if I go to if I tell it 4.64 millimeters of movement, I will get 1 actual millimeter of movement. So if I go to 9.28, let's check the linearity. I'm going to go to minus 9.28, and what we should do is end up on the edge of that marker right there, which will be two full millimeters of movement away from the center point. And we'll see how close that is. Closer, 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 and stop. There we go. Maybe it overshot very slightly. I think it is closer to 4.63.
I think it is closer to minus 4.63.
Yeah, I think you're right. That is slightly overshot. So if I go to minus 9.26, that gets us pretty much on the end. Let's try minus 9.24. That's still just touching the edge. 9.22. Yeah, I think it's around 9.22, which means it is around 4.61 approximately. So if I go to minus 4.61, let's see if it gets us on the edge. But you can see slight variations in the thickness of these because of the chemical etching process that was used to make this PCB. So this should have us end on the edge, on the left edge of the next millimeter marker. Here it comes. There we go. Right on the left edge of the next millimeter marker. Yeah. Just maker said, how many steps do you have for 1 millimeter now? Then just change current steps per millimeter times 4.63 equals new steps per millimeter. Wagonlane says, can you map the movement scale so they are 1-to-1? Yeah, okay, so you're talking about the same sort of thing. All right, so part of this is that in the software, Vic needs to lie to the slicer, or lie to the software to account for the fact that it doesn't like tiny, tiny, tiny little numbers in its coordinates.
At Grant Meisel said, not only is the etching on the ruler imperfect, but screw manufacturers are not after perfect threads.
Yeah, that's right. Yep, so we are very much pushing the limits of physical reality here, or of what I can achieve with a physical thing. So we would call it calibration. Yeah.
We could call it calibration.
We could. Now, let's have a look at the motor 2 value. So we got steps per angle, 0.9 degrees, and travel per revolution, 1.0 millimeters. So this, I would need to change. Tinker. Next level down the rabbit hole for Vic, machine custom screws. Now, I was telling it to move 4. What if you got a screw with finer pitch? Yeah. Gearing, says John Whips. Yeah, the gearing in this is coming from the cantilever mechanism that is doing the 80-to-1 reduction. Grant says the screw thread pitch is 0.5, not 1 millimeter. Yeah.
At Grant Meisel said, the screw thread pitch is 0.5 millimeters, not 1 millimeter.
Yeah, okay, so 1 divided by 4.61 is 0.21692. So if I say $2TR, is this 0? No, first I'm going to 0 this because I do not want to screw this up. All right, I'm going to 0 the axis so that I know that it is in its unstressed position. There we go. So it is now just touching the edge of that track. And if I do 2TR equals 0. I'm not even sure if it's going to handle this. 21692. TR? 2TR. Unrecognized command or config name. Let's just try backing it off and make it 217. Is it going to accept that? No. Is it going to accept 0.2? No. Is it going to accept 1? $TR. Oh, of course. What I want to do, it's 2TR. Oh, I'm an idiot. Let's do $2TR, see if that works. Okay, so we've got 0.2169 millimeters travel per revolution. Now, let's try going to G0Y. I'm going to go 0.5, just in case I have totally screwed this up. So this should move 0.5 of a millimeter in reality. I think it did. And let's see if we go to minus 0.5. Moves it across to there. And if we go to minus 1, it should take us to the edge of the next mark. Boom! There we go. So we now have a direct one-to-one correlation. So if I go back to 0, may need a little bit more calibration, but it's in the ballpark. So that's 0, and if I go to minus 1, it goes to there. Yeah, the actual axis travel direction is reversed. And also remember, I am currently running the y-axis driver, controlling the x-axis stepper. So things are going to need to move around once the other axis is attached. What I don't know is whether Gav is still coming. Because he said a little while ago he was still in Preston, which is the other side of the world. And I was planning to have been gone from here some time ago. Okay, Vic says, so now tweak the scaling so it moves 1 unit as 1 micron.
So now tweak the scaling so it moves 1 unit as 1 micron.
Okay. So then I just divide it by what? Coming. Okay. Like, are you an hour away or are you around the corner?
Proof of function concept has been achieved.
Because I was planning to have been gone from here well before now. Oh, okay. Gav will be 10 minutes away. All right, if he left back when... Yep. So... Now, a factor of 1,000 times more steps. Yep.
At Tinker001 said, Preston, Ontario really is the other side of the world.
Yeah, Preston, Ontario would be. Okay. Bays. Oh, okay. Gav is getting close. Very close. So I will wrap this up in a second. Now, I've got to get my head around this calibration. Multiply, divide. So, if I do $2TR, it is currently 0.2169 millimeters per whatever. Travel per revolution. So that is how much it travels per revolution. So now, in order to use the control system, I need to change this so that if I tell it to move 1 millimeter, it actually moves 1 micron. Is that correct? It's held in JSON so it can be remote calibrated. Oof. Okay, Wagonload says, I'm working on a system where the calibration factor is held in JSON so it can be remote calibrated. Yep, okay. Cool, so I need to divide that by 1,000, essentially. So what I need to do is say $2TR equals 0.2169
At Grant Meisel said, if you are not sure,
1,
try a
2,
factor of 2 first so
3.
you don't break what you have made.
2, 1, 6, 9. Yeah, that's true. That would be a sensible thing to do. Or if I tell it to move 1 millimeter and it moves a micron, so I need to do it the other way around, don't I? Multiply by 1,000. So yes, I think so. So what I need to do is make it, yeah, the other way. Exactly. So I need to make it that. Multiplied by 1,000, it was 0.2 that. So make it 216.9. Okay. So 216.9 millimeters per revolution. So now if I tell it to move 1 millimeter, yeah, careful, says Crispian. A whoops is being made, says Crispian. Yep. And Vic says my brain gets lost there often too. So now, if I tell it to move 1 millimeter, it is going to output fewer steps and it will move less distance. Before I actually get it to make a move, yeah, you need to convert from the number the software accepts to a number the RepRap needs. I'm not going to actually tell it to move until I have thought this through. So previously, if I told it to move 1 millimeter, it would send a certain number of steps and move 1 millimeter. Now, if I tell it to move 1 millimeter, it is going to travel, it is going to output fewer steps and move less. So I think this is now correct. Yeah, so now if I do 0, oh, was it at, had I put it to -1?
I used to do lots of these calculations for the inch-gear ratios of my bicycle.
Yeah, so telling it...
At Tinker001
Yeah.
said, telling it move 1 should now mean move 1/1000th of a mm.
Yeah, that's right. So I'm going to undo this. I'm going to say, I'm going to go back to this. And then I'm going to G0Y0, which is going to put it back to our starting point. Okay, so this is now at our starting point. And then I'm going to set the 692. I'm going to do, not that one, that one. 21692. Okay, that. So now if I do that, nothing will happen. But if I do, just to be on the safe side, I'm going to go 0.1. Ooh, I think it's working. I think it's working. All right, so now if I do Y1, yeah, you can safely test with a move of 0.001. Yeah, I did a test with a move of 0.1. So now, all right, to tell it to go to 0.01 and see if it orbits. Also, it will run slower, so you need to speed it up, says Vic. Okay, I'm going to tell it to move to 1. Yeah, it's moving very slowly. So that, in theory, moved 1 micron. Oh, you can, I think you can you see it moving? I don't know. No, I don't think you can. I can hear the steps going. Do, 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 do. Let's try going 10 microns. It's going to take a while. I don't think I can see it moving. Oh, maybe that gap is getting very slightly larger. It's hard to tell. G'day, Gav. Hey. Gav is here. Okay, so it's halfway there. I am definitely going to have to speed this up. Look how slowly that is getting there. And...
At Tinker001 said, try 10, then 100, then 1000.
Yeah, but it's going to take a long time. I think you can actually tell. If you look at the gap there between the edge of the window and the edge of that, it has very slightly increased. And now...
Hello, Gavin.
Hey guys.
Hello. I'm going to move it back to 0. And then I'm going to end the stream. But let's move this and watch it. See if you can see any movement from the edge of this to the edge of the window. And go. Right, so from starting to... So it should have moved 2 microns now. And coming up on 5 microns. I don't think I can see it. And
Show and tell the new gear.
not yet, not yet. 1 micron and 0 microns. So we should have just done a 10 micron move. Nice. Okay. That is a really cool achievement. So let's stop there for now.
At Grant Meisel said, need a better ruler.
Yeah, I need a better ruler. What I need is a microscope calibration slide. You can get microscope slides that have been, I don't know how they do it, but they have been etched with tiny little markings down in the, multiples of microns range, so that you can actually see the scale of blood cells and those sorts of things when you're looking at them through microscopes. So if I had a calibration slide with
Pretty
graduated
funny to use
markings,
a ruler to measure microns.
yeah. If I had a graduated microscope calibration slide, we could put it on there and see how small a micron really is. But this is kind of beyond our ability to magnify to that scale now. We are down below the limits of perception. Okay. Nice. That's really fun. It's satisfying getting it to that point. I need to increase the speed of the driver so that it actually moves at a reasonable speed now at these factors, and attach the other axes. But it is now time to stop and check out what Gavin has brought me, which is going to be featured in the future once I get onto doing security systems set up around here. Yeah. Oh, Timmer says, needs auto speed control derived from travel distance.
Cheers all. Uru.
Potentially. It's also a matter of the pulses per second that the stepper driver can achieve. So that and the acceleration value, there are a whole lot of config options that can be put into the Tiny G. So I need to mess around with those to tune it all up now and get the X and Y axes both working properly. So awesome. Thanks everybody for coming, and I'm going to have a chat to Gavin, and I will see you all, next week. I forgot. Next week I'm going to be in Canberra on Sunday morning. Ooh, I may not be able to stream. I may stream. I will have my laptop with me, but I'm not going to have anything else. So it could end up being a stream of sitting there on my laptop and doing stuff. I don't know. I will be in a hotel room.
Gavin.
Yeah, I'll be in a hotel room in Canberra somewhere. So remember, push-up challenge. I put the URL in there earlier, and hopefully I will see you from the Berra next Sunday. But I may not be able to stream. It just depends on what the circumstances are of timing and what's going on at the time and all of that sort of thing. And inclination. I may just not have the inclination to do it if there are other things going on and I'm busy. So we shall see. Thank you very much, and have an awesome week, and I will talk to you soon. See ya.